Good evening, everyone. Let's start today's session. Uh, this is for the NPTEL course EMI, EMC, and Signal Integrity. This is week problem solving session for the week 2. The course ID is NOC26EE42, and the course instructor is Professor Amitabha Bhattacharya from IIT Kharagpur, and I am a PMRF TA for the course. I am Rahul Chaudhary from IIT Madras. So this is the live problem solving session for the week 2. So in this we will be solving few problems which are related to this week's assignment, week second's assignment problems. So we'll be solving few problems which are similar to that, but not exactly the same problems. So if you guys have any doubt also, you can unmute yourself and ask me during the session. So let's start today's session. So first we'll start with a brief summary of what has been covered in this week. So in week 2, Professor have covered response of linear. Just a second, some people are joining. I will let them in. Okay. So those who have joined right now, this is a live problem solving session for the course EMI, EMC, and Signal Integrity. This is for the week 2. So we'll start with a brief summary of what has been covered in this week. So first, the lecture 6 started with the response of linear system to periodic input signals. So that was something like, suppose this is a linear system. This is x of t is the input and y of t is the output. So this is a single input, single output, and in EMI, EMC, just a second. So if you have any doubt, you can unmute yourself and ask me any question if you have. But if you don't have any question, you please keep yourself mute. So in EMI, EMC, we are concerned about periodic signals only. Let's say if this x of t is, suppose this x of t which is input for this linear system is, let's say it's a sinusoidal signal, maybe sine or cos. Let's say x of t is something like amplitude x cos omega t plus p. So The y of t will be y cos omega t plus phi y. So if in the frequency domain, if we want to find out this h of omega, which is the response of the system, or we can say this is a transfer function which is given by h of j omega magnitude and its angle h of j omega. So that has been covered during the lecture 6, and then in next lectures professor have covered important computational techniques. So some techniques from signals and systems he have discussed. So some a few properties. So the first property was linearity property, which says that any signal we can write it as a components, like x of t can be decomposed into a1 x1 of t plus a2 x2 of t and so on, if it is a periodic signal. And the second property, so this x of t in the linearity property, we can write this as a, with n can vary from minus infinity to infinity, cn e to the power jn omega naught t. Second was a time shifting property. So these all are just a refresher for you guys. I am sure you guys have already gone through the signals and systems. So these all properties have been covered there, and professor have also covered in the lecture 7. So I'm just giving a brief overview of what are these properties. Are time shift property. So it states that if let's say this is a signal A, 0 and B. So its maxima is happening this x of t time t. So the maxima of the signal is happening at B, and if we shift it, means if we shift it in the time domain by in the time axis by minus alpha, so the signal will be shifted, right? So now it will become something like that. So the signal is advanced. That's what we are called. That's what we call this in signals and systems. So what it become now is a b plus alpha and a plus alpha. So these properties are used in the next part when we are trying to find out the faster way to compute Fourier coefficient of a clock signal. So all these properties will be used there. So and the third property that was discussed was the unit impulse function. So I'm just giving a brief overview. So unit impulse function, which is a direct delta function, we can write this as it's 0 everywhere. Its amplitude is 1 when time is 0. Rest everywhere else it is 0. So this direct delta function or unit impulse function is something like this. Its amplitude is 1 time delta of t. So it's unit impulse function, and it's also denoted as 0 to left hand side, and this integration is always 1 because this is unit amplitude. So those who have joined now, just we are going through the summary of what has been covered in the week 2. So now we are discussing about the important computational techniques that professor has discussed in the lecture 7. So three properties that he have discussed from system signals and systems is linearity property, time shifting property, and unit impulse function. Now if we shift it with time, so if this delta of t is shifted by, let's say, some alpha, t minus alpha, t minus delta, sorry, I will rewrite this, delta t minus alpha and time t, so I will draw on a different color. So now if it has been shifted, means this impulse is happening at alpha instead of 0. So those who have joined now are just discussing the summary of what has been covered in the week 2. So now we are discussing unit impulse function. So now it has been shifted by alpha. So now what we have, it will be written as minus alpha to alpha plus. So it's like just a left hand side and right hand side of 0. Similarly, right hand side of alpha, left hand side and right hand side of alpha, delta t by dt, this amplitude will also will be 1. So this integral will be 1. And one important property will be that let's consider a train of unit impulse function, means like lot of unit impulse functions are there at time t, delta of t, or let's say we can write this as x of t, because delta of t denotes unit impulse function. Now we are not talking about unit impulse function, we are talking about a train of unit impulse functions, or just a impulse function. So this amplitude, if it is unit impulse function, the amplitude will be 1. So this 1 in the bracket denotes the amplitude of this pulse. So this is x of t. So if I write the coefficients of this, will be calculated using 1 by t. So if I writing the Fourier series 0 to t delta t dt, sorry, e to the power minus jn omega naught t dt. When you solve this, you will get 1 by t. 1 by t in the case of unit impulse function. If it is a pulse train of unit impulse function. So I'm just giving a brief overview that it will be useful while we are solving the problems. So instead, if it has been a different pulse, a impulse function but not of unit impulse function, then let's say if that amplitude have been a, then for that Cn will be a by t. And in lecture 8th and 8th and 9th, professor has discussed faster way to compute a Fourier coefficient for clock signals. So he, instead of doing what we have done in the previous lecture, in the previous assignment problems, like we were solving the Fourier coefficients, like Cn is equals to 1 by t t1 to t1 plus t x of t to the power minus jn omega naught t dt. If this x of t is complex, means not easy to solve, then this is a tedious task. It takes a lot of time to calculate this integral. So instead of doing this, professor has discussed a fast way to compute Fourier coefficients for clock signals, because in EMI EMC we will be only considering about, we are worried about this. Our aim is to study these signals, clock signals. So we are not worried about any other kind of a signal. So that's why we are just focusing on this thing. And then as we move forward, you will see instead of having this pulse train like this, we will be concerned about the trapezoidal signal, because that's what actual signal looks like. It's difficult to have something like this, a rectangular pulse. Some rise time, fall time will be there. Actually this signal looks like this is actual. So any clock signal will be something like this. That's why you must have seen in lecture 9 and 10 we were professor was discussing about this trapezoidal pulse signal. So now he discussed about the fast way to compute Fourier coefficient for clock signal. So he gave an algorithm that was, we have to repeatedly differentiate the waveform until the periodic pulse train comes, and then we have to check whether all the impulse train, all are in impulse train. Let's say if we have this kind of a pulse x of t and we want to Fourier coefficients for this, so it's a periodic signal, so it's repeating. So if we want to calculate its Fourier coefficient in this algorithm, what we have to do, we have to find this dx by dt, which will be combination of x1 of t plus x2 of t. So if we take a differentiation, first order differential of this pulse, of this periodic signal, we will get impulse impulse train like this. So if this is a rise time, so something like this we will get. So the positive ones will be our x1 of t, and x2 of t will be the negative impulses like this. So it's sum of this, dx by dt is sum of this. So we have to determine the Fourier coefficient for the impulse train part, which is very simple, that we have seen earlier also. It will be something like this, a by t. And if the time shifting is happening, let's say in x1 no time shifting is happening, and in x2 of t there is some time shifting which is happening. So for that also we will use these properties that we have discussed. And then we have to continue to differentiate until the non-impulse periodic part becomes an impulse train. Then we have to check whether all the impulse, all signals are in impulse after the differentiation. If it is not, then we have to again take the differentiation of that part, and we have to repeat this process till all differentiated waveform are only periodic impulse trains. That becomes more clear when we solve the problems. So we have to divide each part by the required power of Jn omega naught. If it is a first order differential, it will be 1 by Jn omega naught. If it is second order, 1 by Jn omega naught whole square, to return to the Fourier coefficient to the original function. So I hope you get a brief idea what has been discussed. It's just a quick revision for you, because I hope everybody has seen the lectures for the week 2, because that will be more beneficial if you do that before coming to this session. So now let's start with question number 1. So for question 1 to 3 there is a common data, means the waveform is common for all questions from 1 to 3. So consider a periodic waveform defined by x of t as a when it is in between 0 to tau, and x of t is 0 when it is between tau to t. Now if you see, this is just x of t and it's a periodic waveform. That means it is repeating after every t. T means capital T, it's a period. So like I will give you a minute or so just to go through the question and understand. If you have any doubt in the question itself, just let me know. So in the question number 1 we have to find which of the following is the correct expression of Cn. Cn is the Fourier coefficient, so that means we have to find the Fourier coefficient for this x of t. Okay, I hope the question is clear. Okay, so those who have joined just now, we just started the question number 1. So question number 1 is consider a periodic waveform defined by x of t, and now in question 1 we have to find which of the following is the correct expression for Cn, where Cn is the Fourier coefficient. So I hope the question is clear. Now let's start with the solution for this one. So first of all we'll figure out, we try to draw the signal itself, because we will use the faster way to solve, because there was a faster way to compute Fourier coefficient for the clock signal that we just discussed. We will try to use this for this one instead of directly solving the Fourier coefficients. So we'll start with the x of t is given as it's a when it is in between t to tau, and it's 0 when it is in between tau to capital T. Now let's first draw the signal x of t. Okay, I will use this color. This is t, x of t. So x of t is a, as its amplitude is a when it is in between tau, and between tau to t it is 0. So 0, it is like this, and then it is 0. Then it repeats after t. So this capital T is a time period. That means it's a periodic signal which repeats after every t. So here this is t plus tau, so on. So same on this side also. So here this is minus t, and this is minus t. Sorry about that, there was some delay in that. So this will be minus t plus tau, minus t plus tau. So this is our original waveform, and this in question number 1 we have to find the expression for Cn. Cn is the Fourier coefficient. So for the given waveform, that is x of t, we differentiate. So that is the faster way, right? The algorithm that we have discussed, the first step is in that is we have to differentiate this x of t. We differentiate it once to get dx of t by dx of dt, dx of x of t by dt. So I will rewrite this. x of t by dt, and we'll write this in the form x1 of t plus x2 of t. So our aim is here to bring this x of t by differentiating in the form of two pulse trains, x1 of t and x2 of t. So now if we differentiate x1 x of t, I will redraw that here. Let's say this is our x of t. So this is a rectangular pulse train, 0 tau t minus t plus tau, and here t plus tau. So and it repeats, so on. So now what we have done is we have taken a differentiation x of t, dx of t by dt. We have differentiated it. So now I'll draw it. So if we take the differentiation of this, so it's from 0, so this amplitude here is a. So from 0, this is a rising pulse, means this pulse is rising, then it is constant till tau, and it falls down. So when we take differentiation at 0, it will be an impulse, this amplitude is a, and at tau it is an impulse whose amplitude is in the negative direction, and at t and between 0 to tau it is 0, because the constant, if we take a differentiation of constant, it becomes 0, it is 0. So this is happening at tau, and at t again there is this impulse of amplitude a, and this thing will repeat. So those who have joined now, we are solving question number 1, in where we have given x of t a signal, a periodic pulse train, and we have to find the correct expression. These 4 options are given, and out of this you have to select the correct option for the correct expression of Cn, which is a Fourier coefficient, and we are using this faster way to compute Fourier coefficient for this clock signal, which has been discussed by professor. So we have already taken, we have to written this in the form x of t, we have to differentiate, and we have to write it in dx of dt in the form x1t plus x2t, where x1t and x2t should be in impulse, in the form of impulse train. So we have taken the differentiation of this. So now we just have to do dx of t by dt in the form x1 of t plus x2 of t. So if we see, we can draw this as we can write this as x1 of t. So x1 of t is the, it contains all the positive impulses. A and so on. 0, t, minus t, and in bracket I am writing the amplitude a, and x or x2 of t will be x2 of t will have these negative impulses. So I am doing nothing, but I am just dividing it into the positive and negative impulses for dx t by dt. So this has been divided into this. This is x1, this is x2. So negative impulses are happening at tau. This is t plus tau, and again this will be happening at minus t plus tau. This amplitude I'm writing a. So actually it is minus a because it is in the negative direction, right? It came because the rising pulse and falling pulse. If you take the differentiation of this, it will come like something like this. So we'll go to the next page. So here we have seen x1t. This is our x1 of t. So x1 of t is impulse train with time period capital T, and its coefficients can be written as this came from the impulse property. So Cn and C1n, sorry, it should be C1n. So this should be C1 or C1n, and in the subscript we are writing 1 because it's a first order differentiation. So it is given by A of t. So that's what I was discussing here. If it is Cn is 1 by t in case of unit impulse function. If it is an impulse function with some amplitude a, Cn will be a by t. I hope you can hear me. If you have any doubt until this part, just let me know. So if it is fine, then we can continue. So C1, so this x1 of t is the coefficient we can write as a by t, and the superscript, I'll write it here, the superscript which is 1 denotes the numbers or the number of times the original waveform is differentiated. And similarly for x2 of t, it's also impulse train. It's another impulse train which is shifted by an amount tau. X2 of t is also another impulse train which is shifted by an amount shifted by an amount tau. Shifted by an amount.
Can we sit here and work on
Yeah.
the book?
So I am taking one class, so I will talk you after that. You can. So sorry about that. So this x2 of t is also another impulse train which is shifted by an amount tau. So now what we are doing here is we are using two properties. We are going to use two properties, impulse one and the time shifting property. So if we will see, so whose coefficients can be written as can be written as C2n. This one subscript means it's another because the original waveform is differentiated only once. So I'm writing C1 of, so it can be written as, since the amplitude was negative, here if you see A is in the negative direction for x2 of t, we will write it as minus A by tau. So since it was plus A by tau, and now there is a shifting also happened. Look, instead of starting at 0, it is starting from tau. So there is a shifting. It's shifted by tau. So by using this time shift property, we can write this as, this coefficient will be written as e to the power minus j n omega naught and tau. Tau is the amount by how much it has been shifted. So therefore, this Cn we can write as 1 by j n omega naught a by tau. So I am writing j n by omega naught because it has been differentiated, and the power is only 1 because it has been differentiated once. This is because of x1 of t, and the second part will be, okay, so I will write it in this format first, so it is easier to understand. So Cn is equals to C1 n prescript 1 and plus Jn omega naught C2n, because this came from x2 of t, this one came from x1 of t. Both are differentiated once. So this is Cn. So this is Cn. We can write this now. C1 of n we have already seen. This is A by t, and C2 of t is Cn. C2n is this. So now we will just substitute it here. So I will write Cn as 1 by Jn omega naught, and C1n is A by t plus 1 by Jn omega naught minus A by t into e to the power minus Jn omega naught tau. So we can write Cn as, so we can take A common, A by t common, and Jn omega naught also can be taken outside. Jn omega naught A by t, and I can write this as 1 minus e to the power minus Jn omega naught tau. Now we want to write it in the form of sinc. So we can do one thing here. We can take A by Jn omega naught t and take e to the power minus Jn omega naught tau by 2 as common. So here this 1 will become e to the power Jn omega naught tau by 2. If we multiply them, it 1. So that's what we have done. And here this will become minus e to the power minus Jn omega naught tau by 2. So this part we can write it as Jn omega naught t into e to the power minus Jn omega naught tau by 2. So this will become here, and because of this we can write this as here as it can be written as Jn omega naught tau sine 1 by 2 n omega naught tau divided by 1 by 2 n omega naught tau. So, and this we know that sine x by x can be written as sinc x. So I will simply rewrite this as, and this part will get cancelled out, and we can rewrite this as a tau by t e to the power minus Jn omega naught tau by 2 as a sinc function, sinc n omega naught tau by 2. So, but in the options, if we see, the options are given in, instead of omega naught it is given in t. So we can substitute, because we know that omega naught is 2 pi by t. So if we replace omega naught with 2 pi by t in this Cn, so in the above equation if we replace it, we will get Cn as a tau by t e to the power minus jn pi tau by t. So I have replaced omega naught with 2 pi by t, and here sin n pi tau by t. So now if you match with the given option, so this is the required solution for the correct expression of Cn for the given x of t. So if you match it with the given option, the correct option here is C. So if you have any doubt in this problem, please let me know. So this question can have should have been done, like hardly it will take 5 minutes, but I took some time just to explain you guys. Otherwise it's pretty simple. Like if you have any doubt, still have any doubt in this, please let me know. I can explain it again.
Sir, can you explain the slide once more where this
Yeah,
graph is being split into 3 parts?
yeah, sure. So like we professor discussed a faster way to compute Fourier coefficient for clock signals. So instead of simply writing the equations and computing it, there is a way to do it. So we plotted the x of t, and then we took the differentiation of x of t. So dx of dt, and it can be written in two parts, x1 of t and x2 of t. If you take a differentiation, we will get some impulses. Until this part here is clear, right? Dx of dt is clear. This part is clear, like how we got this.
Yes, sir, it's differentiation of the first
Yes,
initial.
yes. And then I divided into using there is one property in signals and system called linearity property. So any signal can be, the periodic signal can be written in this form. It can be decomposed. It's a summation, so into two different signals. So same thing I have done it here using this linearity property. I have written it, I can write this dx of dt, which is this signal. I can divide it into x1 of t, x2 of t. Now if you see, how can we divide this? Because this is impulse, we have written the positive impulses as x1 of t. So, and then x2 of t is all the negative impulses. We did it because we already know the impulse for Fourier coefficient for impulse signals. Impulse signals. It's pretty simple. For an impulse, unit impulse function, Cn is, if it is positive, is a by t, and sorry, 1 by t. And for here in this case, the amplitude, this bracket denotes the amplitude, so Cn will be a by t. And since x of t is negative and it is instead starting from 0, it is starting from tau, which is shifted by tau. So now we will be using this time shift property. So because of that, x, and then this Fourier coefficient Cn can be divided as 1 by j n omega naught. This came because we took the differentiation, first order differentiation. So in frequencies domain, we have to write this in this form, j n omega naught. So 1, this came from x1, and this c2n is a coefficient for x2. So that's why I have done that. Now it becomes relatively very easy. Instead of solving the if we directly find the Fourier coefficient, we have to write this, we have to solve this equation 1 by t, t1 plus t x of t e to the power minus j n omega naught t dt. Since this impulse is a rectangular impulse, rectangular pulse train, we can easily solve this part also, it's not difficult. But what about if we are using some, if x of t is a complex, something like this, then it becomes very difficult if it is something like this. So that's why we are using this algorithm as a faster way to find the Fourier coefficient for this clock signal that we are using. And then simply we just have to substitute the value of c1, which c1 now substitute 1 is a by t and c2 is minus a by t e to the power minus j n omega naught t. So this part came because of we have done that shifting. It came from time shift property, and this minus is because x2 of t is in this negative. So that's why. And then final, this Fourier coefficient of x of t is given by this. Now just simply substitute c1n and c2n, and then we will get this, the final answer, x cn. So I hope this is clear. If you have any doubt in this, please let me know. Is it clear, right?
Yes, sir. Thank you.
Yeah. If you still have some doubt, just did you watch the lectures for week 2? Please go through the lectures also once. Okay, now if it is clear, then we'll move on to question number 2. So question number 2 is also for the signal is same. For question 1, 2, 3, we are using the same data x of t. Now in question 2, if a is given as 1, a means that amplitude of x of t that we plotted. So our x of t was something like this. X of t, I'm just plotting it again. So now instead of a, we know the amplitude, it's 1. And this tau is also given, this tau, and this is the t. Tau is given as 1 second, and time period of this periodic signal is 1.5 seconds. So now we have, in this problem, we have to determine the value of c1n of 1. So it's pretty simple, right? Because you already done it for this. c1 of n means x1 of t. After differentiation, x1 of t is c1 of n. So we already know the formula for this. It is a by t, because if I put x1 of t, it's nothing but this impulse train. Now it is a unit impulse train because this is 1, so which is repeating after every time period t. And here, since a is given as 1 and time period is given as 1.5, so this is our c1n, and when we solve this, it comes around 0.667, or simply because in the option it is given as 0.67, we can write this as 0.67 hertz. So the correct option is C. So if you have any doubt in this question number 2, please let me know. Since you may be finding it difficult because of the handwriting also, it's difficult to write in this PowerPoint, and the pen is also not responding very well. So after this session is over, I will record the session, and also I will upload some handwritten notes, handwritten solutions of these problems, which you can find in the NPTEL portal. So in the portal it looks something like, I will show you how it looks once we'll solve all the problems. But I hope this problem is clear, right? So here the correct option is I'm just going slowly because it's easier for you to understand, and you can also have a pen paper with you and solve along with me. Correct option is C. And question 3, it also using the same x of t. So it's a common data for 1, 2, 3. If A is solution, here A is given as 1, tau is given as 0.5 seconds, and time period t is 2 seconds. In the problem they are asking to find Cn for the third harmonic, so we have to find Cn for third harmonics. So third harmonics means n is 3 here, and in the first problem itself we have find a general notation for Cn for this x of t. So in this problem 3 they are simply asking, question 3 they have asked C of 3. So here what, and they have also given the value of A, tau and t. So now just simply we have to substitute n as 3 and A as whatever is given in the problem. So and from previous question we know the expression of Cn is Cn is given by, for the x of t, this rectangular pulse is given by A tau by t into e to the power minus j n pi tau by t sin n pi tau by t. Now we have to substitute whatever is given in the problem, substituting A as 1, n as 3, because we have to find the third harmonic, means n is 3, tau is 0.5 seconds, and the time period of this periodic pulse is 2 seconds. That's what is given in the problem. Now if we substitute this in the above equation, we get C3s. So if we put A as 1, tau is 0.5 and t as 2, so which will be 1 by 4 e to the power minus j, n is 3, so 3 pi by 4, and sin 3 pi by 4. But if you see, the options are given in much more confined way, so we have to solve it again. So which will be 1 by 4 e to the power minus j 3 pi by 4, and we know sinc x we can write this as sine x by x, means sine 3 pi by 4 divided by 3 pi by 4. And when we solve this, because we now know what is sine 3 pi by 4, which is 1 by root 2, and this goes to the numerator and 4 gets cancelled, and it remains as 1 by 3 pi e to the power minus j 3 pi by 4, and sine 3 pi by 4 will be 1 by root 2. So I will just simply write this here, 1 by root 2. Just a second. It's 1 by root 2. Now if if you see the options again, still it is not in the e power exponential form, so we have to solve this part also, and I hope everybody knows how to solve it. So using Euler's formula, Euler's identity or Euler's formula, we know that we can write e to the power j theta as cos theta plus j sin theta. I hope everybody remembers this. Now I'm using this here. So our c of 3 can be written as 3 pi into under root, and this e to the power minus j 3 pi by 4. So here our theta is 3 pi by 4. So I can simply write cos or minus 3 pi by 4. So cos minus x is still cos x. So I can write as 3 pi by 4 minus j sin 3 pi by 4. Now we can easily solve it because we know what cos 3 pi by 4 is, which will be 3 pi by root 2 into cos 3 pi by 4 is minus 1 by root 2, and sin 3 pi by 4 is 1 by root 2, and still j is there, so minus j by root 2. So now we can simplify it and rewrite this as minus 3 1 by 3 pi into minus 1 by 2, because this minus root 1 1 by root 2 goes inside, and it becomes minus 1 by 2 minus j by 2. Now here we can take this 2 outside, and it becomes 1 by 6 pi into, and minus also I can take it outside, so it becomes 1 plus j. So this is C3, that is the required answer. Now if we match it with the given solutions, so the correct option is option D, minus 1 by 6 pi into 1 plus j. So just writing the correct option is D. So I hope this is clear. If you have any doubt in this, please let me know. I can go through it once again if you have any doubt in the calculation or any part of the problem. So because question 1, 2, 3 has the same signal x of t, so if you have any doubt in question 1, 2, 3, please let me know. So if it is clear, because there is no need to complete all the problems, it's just whichever problem I am solving you should be able to understand, so I don't have any problem in explaining it again. So I can explain it one more time if you want. If it is if you understand it, it's okay, I can move it to the next problem, otherwise just please let me know. Okay, so if this is clear, we will move on to question number 4. So in question 4, 5 and 4, 5, 6 and 7, in these 4 problems they are using common signal x of t. So consider a trapezoidal pulse governed by the equation x of t a t by tau when it is in between 0 to tau, and the amplitude becomes a once the pulse is in uh, between time tau and t, and here the amplitude is given as 1 volt, and tau is 0.25 seconds, and time period of this periodic pulse is 1 second. So in this question number 4 we have to determine the value of C naught. So they are asking what is C naught. So now let's first for the given. So this is a solution for question number 4. Now what we have to do for the given x of t, first let us plot the periodic signal. You guys also try to plot it. If you have any doubt in this, I am also plotting along with you, so we will see. So if you just have a pen and pencil with you, and try to plot x of t, because that will be important in the next problems, even though it is not much important in the question number 4, but it will be required for question number 5 and 6. So now for the given x of t, first let us plot it. Let us plot the periodic signal x of t. Periodic. So in EMI EMC we are concerned about only the periodic signals. That's why you see we are using this Fourier series. So it is given as x of t is a by t by tau when it is in between 0. So I will use a different color for the axis. X of t, and this x-axis is time axis. So between 0 and tau, it's given as its amplitude will be a, so it will be a t by tau. That means till here it will be like this, and after tau to t its amplitude is a, and since t is the time period of this periodic signal or periodic pulse, it will repeat after this. So here this is t plus tau, and at 2t again it will become like this, so it will repeat again, and so on. And similarly on this negative axis of it will also be like this, it is repeating. So that's what the given signal x of t is. I hope everybody is able to draw the signal. If you have any doubt in this, please let me know. But in question number 4 they are simply asking c naught. So we know what is like how to find the c naught. C naught is given by 1 by t, t1 integral between limits t1 plus t x of t dt. So it's just a simple integral that we can solve. So 1 by t between time 0 to tau, our signal x of t is a t by tau dt plus, and between time period t to tau to t it is a dt. And I hope now everybody can solve this integral. So we will solve this. It will be 1 by t, and when we solve integral a t by tau dt, we will get a t square by 2 tau, and between the limits 0 to tau, plus the second integral which is a dt, so a t, and between the limits tau to capital T, which is the time period. Now when we solve this, we will get 1 by t. So I'm just putting the limits and directly writing it here as, so finally it will come as at minus a tau by 2 c naught. Now we can simplify it further by taking a as common and bringing t inside, so it becomes 1 minus tau by 2t. And in the problem 4 we know because it's given as a is 1, t is 0.25, and capital T is 1 second. So just substituting these values, substituting a as 1 volt, tau as 0.25 seconds, and t as 1 second, we get c naught as 1 multiply 1 minus 0.25 divided by 2. So when we divide 0.25 with 2 is 1 by 8. So 1 into 1 minus 1 by 8. And when we solve this, we will get 7 by 8. So this is the solution. for question number 4. So if you see, the correct option is option number B. Correct option is B. So if you have any doubt in question number 4, please let me know. So if question number 4 is clear, we will move on to question number 5. So the signal is same for as the previous problem. X of t is same, that we have already drawn here. Now they are asking to determine the value of second harmonics. So whenever they are asking second harmonics, means we have to find the Fourier coefficient Cn, means they are asking about some harmonic of this, and if they are asking second harmonic, that means n is 2. So we have to find the second harmonic. So for that we first have to do this, because we have to find the Fourier coefficient, right? So that shortcut way is to find first differentiate this x of t and write it into the form where it is a sum of two impulse trains, x1 of t plus x2 of t. So I hope till here it is clear, right? What we have to do is we have to find Cn, and then we have to substitute the value where n is 2, and then we already know the value for a, t and the tau, which is already given here. A is 1 volt, tau is 0.25 and t is 1 second. So we have already drawn x of t. Okay, I will redraw x of t again. Okay, it's better if I draw in the next page because I need some space. Okay, let's move on to the next page. So I'm just redrawing x of t, that what we have done in question number 4. X of t, just a second. So x of t. So guys, I hope you are also solving this problem along with me. So it will be much easier for you if you do it along with me, and you will get a better understanding. And if you get a doubt also, you can just ask me immediately. So it's better to start solving with me. So now I will just redraw x of t, what we have done in question number 4. So since it is periodic, it will repeat like this. So it's 0 here, this is tau, this is t, and after t it repeats, because this capital T is a time period and it repeats after it. So again this here will be t plus tau, and this will be 2t. Same thing, this will be minus t here, and this will be minus t plus tau. Now since we have to find Cn, or second harmonic, means n is 2, we have to take the differentiation. We have to do the differentiation of x of t. So I will draw the differentiated signal, dx of t by dt over this time. So I'll use another color. Now since if you see this, some slope is there, and this amplitude is here a. Since up to this slope 0 to tau, and the value of this slope is constant, the differentiation will be, this is a constant slope, right? So the differentiation of that will be a by tau, and the slope is here is of this line is a by tau. So this is the amplitude of the differentiation until tau, because if you see after tau it becomes a constant value a. So and the differentiation of a constant value is 0. A is 0. So it stays 0 until it reaches t. So after t, there, if you see, there is a slow rising pulse, and now this is a downward pulse. So for the downward pulse, if it is going down, there is an impulse in the negative direction whose amplitude is a. So here this is t, and between tau to t the signal is 0, and same thing will repeat, because here if you see, this is tau t plus tau, and after till t 2t it is again 0. Then again, since it is like this, there will be an impulse of a, and same thing will repeat. Similarly on this direction also, on the negative x direction or negative t direction, same thing will be repeating. Till here it is 0, then after this till here there is a slope. So and at minus t there will be this impulse of a. So this point is minus t, and this point is minus t plus tau. So here this is our x, a differentiation of xt. Now if you see, there x of t does not only consist of impulses, and again at 0 also, if you see, it is coming down, right? So there at 0 also there will be one impulse here. Now if you see, the second part means x2 is in is a impulse string, but this part top part of x of dx of dt is not an impulse string. So that means you have to take another differentiation. So first I will draw x1 of t. So this dx differentiation of x of t can be divided into two signals. This is the linearity property, x1 x2. So if you see, just a second, somebody is joining. So this x1 of t here is, now I will draw x1 of t. Is this rectangular pulse. This will repeat like this. Zero, tau, t, t plus tau. Similarly minus t plus tau. And here the amplitude is a by tau. So this is x1 of t. Sorry, I forgot to put x1 of t. So this is our x1 of t. So what we are doing is using linearity property, and I am decomposing this differentiation of xt into two signals. If we add them, we will get this, and then the x2 of t is the impulse train. This is x2 of t. So if you look, x2 of t is impulse train. This is 0 at time t, 2t, same at minus t, minus 2t, and it repeats since this is also a periodic impulse train. And here the amplitude is a, so I'm writing it in the bracket, it's negative a. So if you see, x2 is in correct form. We needed it as in a form of impulse train. So x2 of t is correct, but still x2 or x1 of t is still not in the impulse form. That means we have to take differentiation again. We have to differentiate x1 of t. So now we'll move on to the next page. Now for x1 of t, I can write c1n as the first one. I am writing because differentiation is done for one time. The subscript means that I can write and let's say for this x2, because now I've denoted x2 as this impulse train, right? So x2, we know x2 of n simply will be minus a by t into e to the power minus j n omega naught t. Since there is no shifting happening, it starts from 0, only the amplitude is negative, we just simply have to write is minus a by t. This is for the x2. Now for function x1 of t, so x1t is 1 of t is differentiated again, so the expansion coefficient for this one are expansion coefficients. This one means c x1 of t are, so c1n subscript 1, sorry, now subscript will be 2 because we have done a second differentiation also. I haven't plotted that again here, but if we do this differentiation, it will be simple whatever we have done in the problem 1. So it's just a repetition of the question number 1. So here is the rise, fall, rise, fall, rise, fall. Similarly we'll get, if we differentiate x1 of t again, we'll get impulse train, two impulse train, where one will be in the positive direction and one will be in the negative direction, which is shifted by tau. So I won't do it again, I'm just simply rewrite it here as a by tau t. This is for the first part, and for again the negative train which is shifted by tau, we can write this a by tau t e to the power minus gn omega naught tau, because it is shifted by tau. So this is time shift property we have used here. So here we have used two properties. Here we have used the property of linearity, because that's why we have decomposed it here, linearity and time shift. So now we have to write Cn, because now we have C1n and C2n already with us. So Cn is given by 1 by Jn omega naught. It's C2n subscript 1 plus Jn omega naught. This is square because we have done double differentiation for C1n subscript 2. So when we rewrite this, we can write this as 1 by Jn omega naught a by t into e to the power minus gn omega naught t. So this is not needed here because there was no shifting happening. So I can simply should have written it as minus a by t here. So this is minus a by t into 1 by gn omega naught plus 1 by gn omega naught whole square. C1n will be e by tau t minus a by tau t into e to the power minus gn omega naught tau. So our Cn will be in the final form. I am just simply writing it in the final form, j into a by 2 pi n into 1 minus e to the power minus gn pi into tau by t. So now I also replacing omega naught. We know it is 2 pi by t. So I'm just replacing this omega naught also, and we have written it in the sync form, which will come as n omega naught tau by 2. So this is our Fourier coefficient Cn. But now in the problem we have asked to find out the second harmonics, means n should be 2. Now we are substituting the values of a, tau, t and n in the above equation. We will get C2s, because in the problem we already know what is the value of a, tau and t. So it's going to be j by 4 pi into 1 minus e to the power minus j pi by 2 sin pi by 2 divided by pi by 2, because sync x is basically sin x by x. So now when we solve this, we will get 1 by 4 pi into j minus 2 pi. So now if we match it with the given options, the correct answer is option C, 1 by 4 pi into j minus 2 pi. So I hope this question is clear. If you have any doubt in question number 4, please let me know. If it is clear, we will move on to question number we were solving question number 5. We already solved question number 5. Now we will move on to question number 6. 6 also the signal is same, x of t, which have been whatever it has been in question number 4 and 5. The same signal is there, means periodic pulse is there for question number 6, and we have to determine the value of one-sided spectral coefficient. So C3 and the subscript is in superscript is plus. C3 plus, what it means is it's one-sided, means a positive side, one-sided spectral expansion coefficient. So whenever in the problem, if something like this means one-sided expansion spectral coefficient is asked, so what we have to do is we have to first find Cn, and since it is asking for the third harmonic, n is 3, then we have to find from Cn, we have to find C3, and then C3 plus is nothing but 2 times of C3. I hope this is clear. So now we'll solve this problem. Now from the previous question itself, we will directly write the value for Cn, because we know what is the formula from Cn is. So this is the formula for this x of t. So from the previous question, Cn is given as j by 2 pi n into 1 minus e to the power minus j n pi by 4 sin n pi by 4. Now since we have to find C3 plus with the one-sided spectral expansion coefficient for the third harmonics, that means we have to first find out C3. So this is the third harmonics, which is given by, since we have to just replace n as 3, j by 6 pi into 1 minus e to the power minus j 3 pi by 4 sin 3 pi by 4. So C3 will be j by 6 pi into 1 minus, since to solve this e to the power minus j 3 pi by 4 I am using Euler's identity and directly writing it as cos 3 pi by 4 minus j sin 3 pi by 4. We know what is the value for sin 3 pi by 4 is, and and then another sinc term is also there, 1 minus e to the, which is in multiplication with this. So here this is in multiplication. So instead of writing sinc, I am directly writing sin x by x, which is sin 3 pi by 4 divided by 3 pi by 4. And when we solve this, we will get C3 as, I'm just writing the final answer directly, which is 1 by 9 square, 1 by 9 pi square into 1 minus cos 3 pi by 4, which will be minus 1 by root 2 I think, and sin 3 pi by 4 will be 1 by root 2, and when we solve this, we will get j, I am taking common, 1 plus 3 pi by 2, and when we solve this further and write in this format 0.06528, you can use your calculators directly to calculate, like convert this into the polar form to this form. But now in the problem we have to find the one-sided spectral coefficient. So the one-sided spectral coefficient, I hope you guys are also solving along with me. If you face any problem, just let me know. Coefficient for the third harmonics will be given by T3 plus is 2 times of C3 and angle of C3. So it will be 2 multiplied by 0.06528 and angle 100 degrees. So C3 plus is the one-sided spectral coefficient for the third harmonics is 0.13056 angle 100. So this is the correct answer for question number 6. So now we'll check the options. So the option which is matching with this is option number B, angle is 100. So correct option is option B. I hope this is clear. If you have any doubt in question number 6, please let me know. Okay, if it is clear, then we will move on to question number 7. For question number 7 also the signal and the data is same as whatever we are using from question number 4 to 6. So this x of t is same. And in question number 7 we have to determine the value of C1 amplitude divided by C3 amplitude, means the amplitude of first harmonic divided with the amplitude of third harmonic of this signal x of t. So we have to find this. So we will solve this. From the previous question we already know what is the formula for Cn. So from the previous question Cn formula is, I'll just simply rewrite it, j by 2 n pi 2 pi n into 1 minus e to the power minus j n pi by 4 into sinc multiplication sinc n pi by 4. Now the value of first harmonic is first harmonics is, so we are finding these harmonics because in EMI EMC we are worried about till the fifth harmonic or the fourth harmonic of any signal, because then after that there won't be any significant amplitude left. So that's why we are talking about harmonics. The value of first harmonics is C1 is given by j by 2 pi into 1 minus e to the power j pi by 4 and sinc pi by 4. So we can write this as, using the Euler's identity, 1 minus e to the power minus j pi by 4 can be written as cos pi by 4. Pi by 4 means 1 by root cos pi by 4 is 45 degrees, so cos 45 is, and minus sin pi by 4 and multiplied with sin pi by 4 by pi by 4, because sinc we are directly writing as sin x by x. When we solve this we will get C1 as minus 1 by pi square plus j by pi square into minus 1 plus pi by 2, and I will simply, it will be approximately equal to, so if we write it in the polar form, and the magnitude will be equal to approximately equal to 0.1166. Now we have to find the ratio of C1 with C3 amplitude. So in the previous problem, question number 6, we already find out what C3 is. So we already know the value of third harmonics is, C3 is j by 6 pi into minus, I'm just rewriting it simply, 3 pi by 4, but we already have calculated this, sinc 3 pi by 4. So in question number 6 we have calculated what C3 is. C3 is 0.06528. This is the amplitude of C3, so it's approximately equal to 0.06528. So if you compare the amplitude of the first harmonic and the second harmonic, there is a huge difference, right? If the ratio also will take, so we have to take C1 by C3, C1 is 0.1166 divided by 0.06528. When we take this ratio we will get 1.787, which is approximately equals to 1.79. It's almost 2 times. C1 is 2 times of C3 or 1.8 times of C3. So if we check the options, the correct option is 1.79, which is option D. I hope this question is clear. If you have any doubt in question number 7, please let me know. So So in question number 7 we didn't have to do much, we just have to find the ratio of amplitude of C1, magnitude of C1 with magnitude of C3. I hope this is clear. If you have any doubt in this, please let me know. If this is clear, we will move on to question number 8. So question number 8, consider a train of trapezoidal clock with unit amplitude and equal rise time and fall time. If the time period of the pulse and rise time is 1.5 seconds and 0.5 seconds respectively, then determine the phase difference between the two consecutive harmonics of the one-sided spectrum. So if you have watched the lecture 10, already derivation is there for the second week. The derivation, I am not going to derive it again, but I will simply redraw this. So this pulse looks something like this trapezoidal pulse. Since it looking like this, because this rise time and fall time is same here. But if you have seen the trapezoidal pulse that we have used in question number 4 to 7, it was looking something like this, because here the rise time and fall time was not same. That's why it was looking something like this. So here I'm not going to derive again, I'm not going to find Cn and take the differentiation and all, because you already know what is the formula for this, so I'm directly going to use that. And for these kind of standard pulse, at least for this pulse, this trapezoidal clock signal with unit amplitude and equal rise time and fall time, remember these formulas because this will be useful. C0 is 1 and A is 1, and for a trapezoidal pulse, C0 is given as, C0 is calculated as, the formula for C0 is A tau by T, but in the problem C0 is already given. But what we have to find is, if the time period of pulse rise of the pulse and the rise time is 1.5 second and 0.5 second respectively, we have to determine the phase difference between the two consecutive harmonics of the one-sided spectrum. I hope it's clear what the question is trying to ask. But now we will try to find out what the tau is, means the pulse width. We don't know, but we know the value of C0, A and T. So we'll simply substitute the value of C0 is given as 1. A is the amplitude of this thing, this A is also 1, and the time period of this pulse is, means it repeats after every 1.5 seconds, so this is T. So if you see, after every T it repeats, means that is a time period, so T is 1.5 seconds, and this is tau. Here this is tau. So tau comes out to be 1.5 seconds. So whatever I have drawn is not exactly the accurate values. Based on the values, just a rough estimate I have given to showcase you how the pulse looks like. But here, if it is like this, it should not be like this, right? It will be something like this. But we won't be concerned about what the actual waveform looks like. Here our aim is in this problem is to find the phase difference. So now we know the tau. Now we know that for a given trapezoidal pulse, the phase is, so the derivation, if for this you just refer to this lecture 10, because now time is less, I can't derive it. So we know that for the given trapezoidal pulse, the phase is angle Cn is plus minus n pi into tau plus tau r by t. So it came from that sinc, whatever, if you derive it, there will be a sinc term for Cn. Something will be there and there will be a sinc term. From that, whatever the angle is inside that sinc term is, that sinc function, whatever is, this is the angle for this Cn. is plus minus n pi into tau plus tau r into divided by t. So we'll move on to the next page. And the phase difference is given by, but in the problem we have to find the phase difference between the two consecutive harmonics. The phase difference between two consecutive harmonics, C, let's say the first harmonic is Cn plus 1 and the previous one is Cn. So we know already what the formula for Cn is, and for Cn plus 1 it will be, so I'm just simply rewriting this as tau plus tau r divided by t into n plus 1 into pi minus n pi. So this will be the formula for the phase difference between the two consecutive harmonics for a given trapezoidal pulse. So if we simplify it further, I can rewrite this as tau plus tau r divided by t into pi. So tau here is 1.5 plus tau r, the rise time is 0.5 divided by 1.5 into pi. So when you solve this, it comes out to be 4 pi by 3. So but the options are in degrees, so we simply have to convert radians into degrees. So to do that, we just have to multiply it with 180 by pi, and when we do this, the angle in degrees comes out to be 240 degrees. So if we match with the given option, the correct option is option D. Correct option is D. So I hope this question number 8 is clear. If you have any doubt in question 8, please let me know. So if this is fine, then we will move on to question number 9. And for question 9 and 10, they have used the same trapezoidal pulse with time period of 2 seconds and rise time of 1 second. And the phase of the first harmonic is 180 degrees, so it means we have to use the same formula that we have used. The phase of the first harmonic is 180 degree, and the magnitude C3 is given as C3 plus. For the one-sided spectrum, C3 plus is 8 by 9 pi square. Now we have to find we have to calculate pulse width if the rise time and fall time is same. So they are asking about tau. There when the question is asking about pulse width, that means we have to calculate tau. We don't know. We don't know what tau is, so that's what we have to find. And in the problem already it is given that angle of this C1 first harmonic is 180 degrees, and the rise time and fall time is same, which is 1 second, and the total time period, the time period of this periodic pulse is 2 seconds. Now for a trapezoidal pulse with equal rise and fall time, so this formula is for the trapezoidal pulse which has a same rise and fall time. Now for a trapezoidal pulse with equal rise time and fall time, the phase of the nth coefficient is given by, because we already have given what is the phase of this first harmonic is already given. So for any nth coefficient, the formula remains same. If it is 1, 2, 3, doesn't matter, the n value only changes. The phase of the nth coefficient is given by, so this angle Cn is given by plus minus n pi into tau plus tau r by t. Capital T is a time period. So in the problem already we know what C1 is, and C1 formula will be 1 plus minus pi into tau plus tau r by t. And since we already know what C1 is, which is 180 degrees, is equals to, or we can just, instead of writing it in degrees, we can write this in radians, because everything else is in that, in pi terms. So 180 degree we know is pi, which is, and the formula is plus minus pi into tau. We don't know the tau that we have to find, pulse width, plus rise time. We know what is tau r. Tau r is given as 1 in the question, 1 second, and the total time period of the signal pulse is 2 seconds. This the period of the pulse is 2 seconds. And when we calculate, we can easily find out what tau is, pulse width is, and when we solve this we will get 1 second. So if you match with the options, the correct option is option A. I hope this is clear. So directly use the formula for this trapezoidal pulse. It will be helpful in this course if you remember the formula for the trapezoidal pulse, which has equal rise time and fall time. So all these Cn and angle Cn, if you remember these formulas, it will be helpful.
So we consider the plus or minus value of pi when we are solving for tau.
So here you don't have to consider that, because time, time cannot be negative, right? So you should consider only the plus value. If you, let's say if I am getting plus minus 1 second, minus 1 second doesn't make sense physically. So the pulse width cannot be minus 1 second. It can't be, right? That's why I am not considering the negative value here. So because if it is in the negative time axis also, the pulse width still will be 1 second, right? We can't say it is minus 1 second. Minus 1 second doesn't make sense in this. So that's why I have not considered this. I hope this is clear. The correct option for this is A. So if you have any doubt in this, please let me know. So if this is clear, we will move on to question number 10. So question number 10 also is the same pulse. The data is same, but now we have to calculate C naught. Calculate C naught and amplitude of the trapezoidal pulse. That means we have to find C naught and amplitude A. So now we will solve this problem. So what is given here is the magnitude of the third harmonic is given of the one-sided spectrum. C3 plus magnitude is 8 by 9 pi square. Now we know the standard formula for this. We know that the magnitude of the nth Fourier coefficient is given by the magnitude of the nth Fourier coefficient is given by Cn plus is, since I'm writing this Cn plus for the one-sided one, I'm multiplying it with 2 a tau by t sync. So that's what I was saying. Just remember these formulas for this pulse, which has the same rise time and fall time for the trapezoidal pulse, is n pi. Or if you solve a lot of problems, right, you will automatically will remember these formulas are pretty simple, because in EMI EMC now on in all the lectures we will be considering these kind of signals in like these kind of trapezoidal pulse only. Sinc n by tau r. This tau r is the rise time divided by t, because that's what actually is. All these pulse signals are not like this, they are actually something like this physically. So this can be as small as possible, but it can't be immediate, it can't go like this. Something physically, all digital signals are like this. If a good system, they can minimize it as much as possible still, but something will be like this. That's why this EMI EMC is considering this trapezoidal pulse. So now move back to the question. So this is the formula, and we already know what is C3 plus is. So now the two unknowns are A. We don't know what A is. So for the third harmonics, we can just simply rewrite this formula, substitute the values. C3 is given as 8 by 9 pi square, and in the formula 2, A we don't know, tau is 1, capital T is means that the period of this periodic signal is 2, and sinc, so I am writing as sine 3 pi by 2 divided by 3 pi by 2 into sine 3 pi by 2 divided by 3 pi by 2, and when we solve this we will get 4a by 9 pi square. Now we just have to equate these two and then calculate a. So now what we have to equate is 8 by 9 pi square, which is the value of the amplitude of C3 plus, and it should be equal to 4a by 9 pi square. So now when we compute it, we get a as 2. So if it is some unit, that unit we don't know if it is a current signal or a voltage signal, so that's why I'm not writing any unit. So a is 2, and C naught also we have to find. So C naught for a trapezoidal pulse whose rise time and fall time is same as a tau by t. So a is 2, tau is 1, and time period is 2. So C naught is 1. So C naught is 1 and A is 2. This is the answer. Now we'll match the options. So so the correct option is option A. So I hope this is clear. If you have any doubt in these problems that we have solved today, just let me know. We can discuss them again. So I will be also I have recorded this session. I will be uploading it in the YouTube, and the link for that will be available here in the EMI EMC portal, this NPTEL portal. So I will show you how it will look like. So I hope my screen is visible. So if you move on to that week 2, if you see, like, there is a option here for problem solving session January 2026. So if you click on that, it moves you to this problem solving session recordings. So if you click it here, you will direct it to a Google Sheets. So in that sheet, first one is there are two TAs for NPTEL TAs for this course. So I'm taking the session on each Tuesday from 6 to 8. So this is my thing, and the link will be available here, and the recorded and the lecture notes, the notes of the solutions will also be here. So I request you guys to, if you want to rewatch the video or you want the questions and the solutions, you can open this Google Drive and you can access that. And also there is a Google group for this course. So Google discussion forum is there. I request you guys to join that also. So if you find any problem in the assignment questions, if there is some misprinting or something, you can inform it here. You can let me know also, but it's better if you inform directly it here, because you can get a solution faster in that. And if you still have any doubt in the problems that we have solved today, you can email me. My email ID is my email ID is ed22d009 @smail.iitm.ac.in. iitm.ac.in. So this is my email ID, ed22d009 @smail.iitm.ac.in. So just email me if you have any doubt. And from next session, because this was the second week, the deadline for the assignment 1 and assignment 2 is on 4th February. So in the next session on 10th February, we will solve the assignment problems also for us week 1 and 2, because I can't solve the current week assignments because still the due date is there. So after the due date is passed, we will try to solve those questions also, and you can get your doubts clear. So that's all for today. If you have any question, just let me know. Otherwise, this is all for today's session. Thanks for joining.